Started. Good morning, everybody. Welcome to our first session today. We will have a session on microarchitectural security with 3 exciting talks. Our first talk, given by Theo Bitton, will be on call rewinding, efficient backward edge protection. And I think when we're ready, we can get started. All right. Welcome, Theo.
Thanks. Good morning, everyone. So I will be presenting a recent work of my PhD called Call Rewinding Efficient Backward Edge Protection at Thales and Nantes University. So a bit of context before diving into it. So the goal of the PhD is to develop a hardware solution regarding control flow hijacking exploits. So you may know code reuse attacks like return auto programming, jump auto programming. And the goal is to develop these solutions mostly as hardware IPs, hardware solutions with low surface and performance costs. So we aim for lightweight solutions, mostly through microarchitecture modifications or hardware monitoring IPs. And we target embedded systems and specifically the RISC-V architecture. We work on the CVA6, an open source RISC-V core. And this work is supported by the French National Research Agency through the Secure5 project. Okay, so code reuse attacks. These are software attacks that rely on a memory vulnerability. So this is a control flow graph here, where you have the different basic blocks of your program and the edges between the basic blocks. That would be the legit ones here. And as part of one basic block, you have a memory vulnerability that an attacker is able to exploit to create an illegal edge between 2 basic blocks. Right, so that creates a new edge as part of the control flow graph. And by using this first vulnerability, overwriting a pointer, and creating many of these illegal edges by chaining them through indirect jumps in the program, an attacker reuses parts of the applications with gadgets, so short snippets of instructions that end with jumps. And by chaining these many gadgets, they give a new semantic to the application, and that's what we call a call reuse attack. So I first mentioned return auto programming, so ROP, and specifically ROP is based on return addresses overwrites, so exploits of the return address that is stored on the stack. So here on the left, you would have a corrupted stack with the addresses, sorry about that, with the addresses of the gadgets. And here an example gadgets that would be a functional ROP gadget with the different instructions of the gadget and the return instruction that would transfer control to the next gadget. And by chaining all these gadgets, you have your attack. So a solution against these attacks is the shadow stacks. So on the left, you have your regular program stack with the return addresses, the save registers, and the local variables as part of your stack frames. And on the right, you have your shadow stack. So a shadow stack is a copy of the regular stack, either a full copy or only a copy of the return addresses. And it's supposedly stored in a secure memory location. And the goal of the shadow stack is to verify the integrity of the return address when you execute return instructions. So you would pop values from both stacks and then compare those values. So the main issue with shadow stacks is they have a non-negligible impact on performance, especially true for software shadow stacks. And for shadow stacks that are done using ISA extensions or through hardware-assisted implementations, they have a non-trivial inter-process management because you need to have one shadow stack per process, and this can be tricky because you need additional secure memory space all the time. And here in a very recent work of hardware-assisted shadow stack, they had performance overhead from 2 to 14%, and a huge need of hardware resources and memory space to implement the shadow stack. So that's why we come up with a proposal called call rewinding, which is an alternative to shadow stack, and it's based on a property that was already explored in the literature, that return addresses target call preceded instructions. So here on the left, you would have your software program with a call to a function here. And then once you execute this function, you return from it, and you would expect it to target the next instructions after the call. So what we propose with call rewinding is to simply, instead of returning directly on this instruction here, return on the call function and check the type of the instruction at this address. And basically, we can do that through a hardware implementation. So, and we can also leverage branch prediction mechanisms that are very popular mechanisms used in modern CPUs, and mainly the return address stack, which is the module responsible to the acceleration of return instructions in the CPU. So on the left, you have what it would look like. So you have your function call here, and then here, once you execute the call instruction, you push the address +4 on the return address stack, which is a hardware module. So you execute your function, and when you return from it, you would pop the value from your return address stack, and if the value and start fetching instruction at this address. And if the once resolved, the return instruction corresponds to its address, you've won a few cycles here. So what we propose to do with call rewinding is to trust the prediction of the return address stack and only perform the check for mispredicted return addresses. So here you have your mispredicted return address, and call rewinding simply fetches the instruction before that, the rewinded address, LWA, and perform the check. Okay, so how would that look like in the context of a pipeline, right? So here you have a 5-stage pipeline, and we consider using the return address stack and instruction scan. Instruction scan simply means pre-decoding instructions at the fetch stage to know their type and update the branch prediction mechanisms. Okay, so here we have a return instructions, and we consider that the next address is predicted here. So then we execute, we advance the pipeline for a few cycles, and we arrive here at the execution of the return instruction. And here it's the stage where we will resolve the next address. And here we realize that we mispredicted the return address. So all this needs to go away. So with here, we then compute the rewinded address, so the return address -4. And this is where we perform the call check. So we fetch the instruction at RWA. And here, using instruction scan, we get the type of the instruction. So we check if it's a call or not. So the final execution of the return instruction was delayed here to use the result. And depending on the result, either we have an error here, so the instruction at LWA wasn't a call, and we propagate an exception to the return address. Or, on the other case, we resume execution. So in the next cycle, the instruction at LWA is flushed. We don't want to execute it again. We don't want to execute the call instruction or whatever was at this address. And we resume execution at array, so we preserve the program. Okay, so now that I've explained the concept, what do we actually detect with call rewinding? So we were able to detect all illegal return addresses. So I mentioned a ROP earlier, and this is the attack we had in mind when we developed the solution. But in fact, we were able to detect all non-call preceded return addresses. And this is what we call a coarse-grained control flow integrity mechanism, because we were able to match a valid call site, but not the original call site, as a shadow stack would do. So it's not a one-to-one matching, it's a one-to-n matching. And so this leaves few targets for attackers to exploit, right? So here we have an example of a call preceded gadget. So that's the name of the remaining gadget in the application space. So here we have the ROP gadget. Here is the call instruction, and this is now with core rewinding the only target that would be the only instruction that would be target for attackers to use. So for the proof of concept, we implemented core rewinding on the CVA6, so a RISC-V open source core, and it has a C-stage pipeline, so it's similar to the one I presented earlier, and it uses branch prediction mechanisms and the return address tag that I mentioned. So this is a great target to use to implement core rewinding, and it's also capable of booting Linux, which is interesting for to test the solution on a real platform and on FPGA with the Digital Genesis 2. So to test core rewinding, we just adapted the kernel a bit with a custom exception handler in order to just, when we raise exceptions, be able to handle them and stop the execution of the application. So a bit of implementation details at the microarchitectural scope. So the implementation of core rewinding is fairly minimal because we only need to modify the branch unit to perform the computation of the rewinded address. So here it's the stage where we would resolve the jump address, so we know if we mispredicted or not, and we can, if it's the case, compute the rewinded address. So that's the -4 we see here, and then all of this information gets sent to the fetch stage of the CPU, where we would fetch instruction at the rewinded address. And this rewind module here is the one responsible for the aggregation of all the information regarding the instruction type. And here we see if we have the call instruction at the rewinded address or not. And also we're able to send a signal to the next stages to skip the instructions that we don't want to execute. So for the experimental results, so the overhead for core rewinding is fairly minimal. We only have a very low percentage of overhead in LUTs and flip-flops, and very low performance overhead measured using UCB benchmark. So in comparison to software shadow stack, this is very interesting in terms of performance, and compared to hardware-assisted implementation of shadow stack, it's also interesting because we have less performance overhead and less hardware overhead and no memory footprint that would be the result of storing the shadow stacks in the memory. So for the security assessment, we tested with two benchmarks. We used RIPE, which is Runtime Intrusion Prevention Evaluator, that performs a lot of pointers overwrites and a lot of them on the return address, so we were able to test with this benchmark, and also ROP generator, which is a generator of ROP attacks specifically on the RISC-V architecture. And we were able to detect all the attacks generated by those two. But the most important factor is the remaining gadgets usable by attackers. So we measured that with an in-house tool that gets gadgets from applications for the RISC-V architecture. And so we only measured like the difference between the ROP gadget and the call preceded gadgets that we have as part of applications. And we saw that we eliminated 99% of ROP gadgets. So this is quantitative analysis. And qualitative analysis is not something that is part of the literature yet, but the gadgets remaining are longer than the one you would expect for a meaningful attack to be used. So that's also an important factor. So to go further on the implementation of core rewinding, so regarding its impact on the system, so it's enabled in user and machine modes. So in RISC-V you have 3 privilege modes, and it's only not activated in supervisor mode, which is the privilege mode in which the kernel runs, because we had false positive in this privilege mode when we booted Linux. So since the entry point is mainly in user mode when we run applications, this was considered not really a huge factor. But we also had 1 false positive in user mode, and so we had to adapt the exception handler to counter it. So this false positive is identified. It's the sig return handler. So the sig return handler overwrites the return address to an address of a dynamic shared object to perform a system call, and this is not a call preceded address. And yeah, we were able to identify it and bypass this specific false positive, but it might need to, in the future, modify the way this sig return handler is written to not do this type of construct. So the RISC-V ISA has compressed instructions, and this is something that was painful to implement for core winding, since we perform the -4 operation. So when we have compressed instructions, the alignments gets different, and we have to also consider address at -2. And this was responsible for most hardware logic as part of the implementation. So when we support compressed instructions, the override is slightly bigger than without, but both works. And finally, software constructs that are mainly considered problems for shadow stacks has context switches and the long jump set jump construct. So for context switches, since core rewinding is purely hardware and stateless, there is nothing to save as part of context switches. So this is supported by nature. And also the long jump set jump construct, since the set jump instruction sets the address directly after its call instruction. The long jump will return to the address after the set jump. So we will be able to test that and see that it doesn't cause problems either. All right, so to conclude, so core rewinding is very lightweight alternative to shadow stack that we're able to implement and test on target. It has a lower impact on performance and hardware resources. It has no memory footprint, which is something important for embedded systems, and all that for a nearly equivalent security. So we have a few remaining gadgets that we're able to determine that we eliminate 99% of them. And it's adapted for legacy applications. We don't need to analyze the binary before executing them on the platform. And as part of future work, we'd like to study the compatibility of core rewinding with more advanced CPU mechanisms. So recently CVA6 was equipped with dual issue, so that would be something interesting to test, like how is it possible to support core rewinding with this type of construct or with out of order execution. So that concludes my presentation. So thank you for your attention.
Thank you, Theo. Oops, sorry. So we have plenty of room, time for questions. Are there any questions? Yeah, please use the microphones on the hallways.
Hi, good morning. Thanks for the talk. Nice presentation. My question is any tool support needed? Like, does the compiler need to know that the hardware is not the standard hardware or anything?
So for a proof of concept, we didn't use any tool to inform the software that core rewinding was implemented. But if we're taking a more industrial approach, obviously we didn't test every application that is out there. The properties that we are based on is supposed to be respected by the compiler, but probably it's not the case for every application. So if we're thinking more industrial, maybe in fact there would be a need to know that core rewinding is implemented to avoid false positives, for example. But as part of the proof of concept, we were able to boot Linux, execute our benchmarks without knowledge that the security enhancement was implemented.
Okay, thank you.
Okay, there's another question.
Hi, thank you very much for the talk. My question is, would this also work for other instruction set architectures like x86, for example, because there you can have unaligned instructions and then maybe coarse-grained control flow integrity isn't enough?
So for x86, in fact, it's a bit complicated to know if it will work because you have indeed unaligned instructions. But I mean, if the instructions are identified, the one we would need to scan for and decode, I don't see an issue with the mechanism. Maybe it would just have a higher hardware footprint in terms of implementation. But I think the mechanism is more adapted to RISC ISS. Like, for example, ARM would be a close candidate to RISC-V.
Okay, thank you.
So while we wait for other questions, I actually have a question as well. So you basically showed that you wait with the execution until you have identified the address. So for processors with a lot of speculation, what would be the impact? Would the performance be more heavily impacted, or?
Without branch prediction, you mean?
Sorry?
You mean without the branch prediction? How the impact would differ?
Mm-hmm.
So we also evaluated that, and the performance loss is similar because, you don't have, since it's only one cycle or two that it would take to perform the security check, the performance overhead is slightly bigger, like it's just a few thousands of percentage more, but it's the impact is not very different with and without branch prediction.
Okay. And maybe one more question about the attacks that still work out. You already mentioned that the gadgets tend to be longer. Are there other properties that need to be fulfilled? So is it in general less likely to find these gadgets, or what are the main difficulties for an attacker if they are still looking to circumvent the countermeasure?
So the main difficulties would be that you have less gadgets and that they are longer. So it would mean like you have more potential side effects when you use them. And I mean, this is also something we're working on, is to identify the path that are possible for attackers to use, even if they have 100 gadgets, comparison to 10,000. Like we don't really know yet the difference between those two sets of gadgets in terms of quality. Yeah, that's something that we are working on right now to determine like the effectiveness of the solution in terms of something more than quantity, the actual quality of the remaining set of gadgets. But yeah, the size of the gadgets and the fact that you have less of them is already something that is difficult for attackers to perform rob attacks, mostly.
Great, thank you. Are there any more questions? I think we can have one last question.
It's my understanding that this would kind of need, if you would deploy this widely, this would need a change to the instruction set, right? And do you think it's likely that this can happen after RISC-V has been around for quite a while?
Sorry, after what has been around for?
Right, RISC-V already exists, a lot of software and even hardware exists. So do you think it's likely that a change like this, that actually changes the meaning of an instruction, is likely to succeed?
So you have, as part of the RISC-V extensions, you have the shadow stack extension and the landing pad extension that also modify the behavior of the return instruction, for example. So, it's simply like it would be an extension. So, why not, right? So, of course, that would mean change of how the software is compiled, or mechanisms to enable and disable the security check before sensitive parts, for example, where you would have a controlled return instructions that does not adhere to the property. But yeah, if it's an extension, then why not?
Okay, thanks.
Well, let's thank you again. And with that, we move to our next presentation. It's Cherry Crypt, Transparent Memory Encryption on Capability Architectures, and it will be presented by Jennifer Jackson.
Okay, I'm Jennifer Jackson from the University of Birmingham in the UK, and I'm going to be talking about Cherry Crypt, which is about transparent memory encryption on capability architectures. So I'll start off by talking about the motivation behind the work, with a focus on Cherry capability architectures for trusted enclave execution. And then I'll talk about the transparent memory encryption concept, then the Cherry Crypt hardware design and the results from our proof of concept testing. So the Cherry capability architecture is a hardware-based architecture providing memory safety down at the hardware level and can protect against around 70% of all software vulnerabilities. Cherry itself stands for Capability Hardware Enhanced Risk Instructions and is an instruction set extension for risk-based processors to provide fine-grained access control to memory. And it can protect against vulnerabilities such as buffer overflows, null-pointer dereferences, and other types of out-of-bounds memory issues. So the main concept of Cherry is that pointers are extended to something called capabilities down in the hardware level. So in a non-Cherry system, for example, you might have a pointer that points to a buffer in memory, and the address field of your pointer contains the start of your buffer. And the danger with this type of architecture is that it's possible to point to memory outside of this buffer region using some kind of offset through mistakes in the high-level code. But in your Cherry architecture now, your fields of information are now extended with extra fields with bounds and permissions, and this is called a capability. And this capability creates a controlled boundary around the outside of your buffer region to prevent access to memory outside of these bounds. Now you can map the capability in different ways in different architectures, and the work that we're working on, we've mapped a 32-bit architecture into a 128-bit uncompressed capability. And in this format, our bounds information is represented by these three fields of information. So you have a base, a length, and an offset, and that represents the bounds in which your capability is controlled. You also have a permissions field, and that tells you what you can do within that memory region. So that tells you whether you can execute code or read and write data, for example. You also have this extra tag bit that sits at the end of your capability that tells you whether your capability is valid or not. So if you try to perform an illegal operation that's outside the rules of the Cherry architecture, then this tag bit will automatically be cleared by the hardware, so that when you come to use that capability, it will create a hardware exception. And then this other field here called the O-type, this is used for sealed capabilities, and I'll talk a bit more about that on the next few slides. But essentially, a sealed capability is a capability that points to a memory area, but without direct access to that memory. So the motivation behind the work is to use Cherry for secure enclaved execution. So this is where you have your sensitive data and computation carried out inside a secure region of memory called an enclave, away from the rest of your untrusted operating system and services. And in a Cherry-based trusted enclave environment, we can use these so-called sealed capabilities. And these sealed capabilities create your secure enclave and point to the enclave area without direct access to the memory. And the only way you can run the enclave itself is through a special Cherry invoke instruction to run the enclave code. We also know that these types of trusted execution environments in general are vulnerable to hardware attacks. So an attacker can gain access to the actual raw data in memory. So the idea here for this work was to physically encrypt these capabilities in memory to prevent these attackers from gaining access to the raw data, as well as using the Cherry mechanisms for preventing these software vulnerabilities as well. So one of the benefits of encrypting capabilities is that we can use different encryption keys for the different capabilities, and this prevents overlapping capabilities from gaining access to the same data. And the only way to prevent this at the moment is through complete memory sweeps or using linear capabilities, which are difficult to implement in practice. So in terms of the concept of transparent memory encryption, this can be integrated seamlessly into the Cherry instructions inside the sealing and invoke process. So I'm going to talk about the C-seal instruction and the C-invoke instruction. So I'll start off by just talking about how the seal-invoke process works, and then how we can integrate our encryption into this. So for the Cherry seal process, we start off with two capabilities, a code capability and a data capability. And these point to the code and data section of your enclave, which have been preloaded with your enclave code. And then we have a third capability called a sealing capability. And this contains an O type in the base field of the capability. And this is a unique identifier which is used for your sealing process. And you can think of this sealing capability as a key which locks or unlocks the access to that memory area. So what happens is during the sealing process, the O type is copied into the O type field of both the code and data capabilities. And then this seals both of these into a sealed capability pair so that they can no longer have direct access to these codes and data sections in your enclave. So now when we want to actually run our enclave code, we need to perform a domain transition from our untrusted domain into our trusted enclave domain. And for this, we use the Cherry invoke instruction. So in this process, the instruction checks the O type of both the sealed code capability and the sealed data capability to check that they are the same. And if they are the same, then the sealed code capability gets copied into the program counter capability, and the sealed data capability gets copied into the data register capability, and these are both unsealed. So this creates our domain transition, and now the enclave code is run from the start of that program counter address. So now we want to add our encryption to this process. So the first thing that we need to do is we need to transfer a software permission bit into a hardware permission bit. And this allows us an extra bit to tell us whether we are going to be doing encryption within this seal and invoke process. So when we do our first seal instruction, we look at this encryption bit within the code capability and decide whether we're going to do an encryption. If we are going to do the encryption, we take the sealing O type and use that to generate an encryption key. So we read the data from memory, do the encryption, and then write that back out to the same memory location. And then we do the normal seal operation of our code capability. And so now we have an encrypted sealed capability. So during the encryption process, we also generate some additional authentication tag data and initialization vector, and this is stored at the end of the encrypted data. So at this point, we make an assumption that the bounds of the capability is large enough to accommodate this extra information. And then we shrink the size of our bounds of our capability to just the encrypted data. And then we repeat this process again for our data capability. And here we're using the same O type, so we use the same encryption key. And now we have our sealed encrypted capability pair. We also make two additional assumptions at this point. So we try to, we create a new key every time there's a new O type. And we also create a new key every time we create a new enclave. And the reason for this is to stop the issue where we are presented with the same O type and we want to generate a different key. So now we're going to do the domain transition to the secure enclave region. So what we do here is we look at this encryption bit to decide whether we are dealing with encrypted capabilities. And if we are, we take the O type and retrieve the encryption key. And then we perform the domain transition by copying the code capability into the program counter and unsealing, and the data capability into the data register and unsealing. So now then, when we actually start running the enclave code, we do a partial decryption of both the instructions and the data as and when required until we return out of the enclave and return to the untrusted domain. So that's basically the outline of the encryption. So now I'm going to talk a bit about the actual hardware design of the Cherry crypt. So we designed the encryption engine based around an existing Cherry 32-bit RISC-V FPGA core that was initially developed by KU Leuven and is freely available on a GitHub. So we extended this core. So this processor consists of a standard 5-stage pipeline, which connects to the over the AXI interconnect to the external memory and other peripherals. And our engine sits in between these on the instruction and data bus. So the main control signals from our seal and invoke instructions come from the memory stage and initially connect to the key generation and management unit. And this key generation management unit contains a table which stores the keys against the O types. It also stores the next initialization vector, and it tells you whether the key has already been used once or not. So what happens at the start of the Cherry C instruction? It looks at the O type and determines whether a key doesn't exist or has been used twice. And if this condition is true, then it will generate a new key based on a random number generator and store this key into the table, and then return the key and the initialization vector. If the key has already been used once, so that's when it has already encrypted the code capability, so now we want to encrypt the data capability, it'll simply look up the key in the table and return the key and a new initialization vector. At the end of the encryption process, it will then store the next initialization vector back into the table. So during the encrypted Cherry invoke instruction, it looks at the O-type and matches that into the table. If there's a match, then it will return the key and the initialization vector, so it can do the encryption and decryption as and when required. And then when the enclave returns, when it's finished its code, it will store the next initialization vector into the table. So going back to the high-level design now, so we have the main encryption core, which we've used a AES GCM standard encryption algorithm, and this is connected to our control selectors, which direct the data into the encryption core. So the encryption core can be figured in various different ways, and in our design we've configured a single encryption function and two separate decryption functions. And the reason for this is so that we can simultaneously decrypt both the instructions and the data at the same time. There's a CSEAL encrypt read-write block, which controls the reading and writing of data to and from the encryption core during the encryption process. And we have two caches, an instruction cache and a data cache, and this is used to temporarily store the partial decryption of both the instructions and the data. And they both check the commands on both the instruction and the data buses to make sure that these commands are within the bounds of the current enclave. And if they are within the bounds of the current enclave, then they will extract data from the memory, decrypt it, and load it into the caches to be used as and when required. And this continues until the program counter goes outside the bounds of the enclave memory. So that's an outline of the design. So now I'm going to talk a little bit about the results from our proof of concept testing. So there are a number of results in the paper, but I'm just highlighting two here. So we've got two graphs based on the latency and overhead of the encrypted enclave computation. And we tested this over a range of batch sizes. And what I mean by batch size is that when you do your encryption, you split your data up into fixed size lengths. And each of these is associated with your authentication tag and initialization vector. And we've called this the batch size. And this also corresponds to the size of a cache line in your cache memory. So we've tested this with two enclave programs, a more complex program where we are decrypting instructions and also decrypting and encrypting data. And then a second program where we are just decrypting only instructions. So in the first graph, the grey lines are the latency without encryption, and the black lines are the latency with encryption. So we can see that for very small batch sizes, there's a very large latency, and that's because of having to constantly read data from memory and decrypt. And so we found that the optimal batch size was about 1 kilobyte. For the overheads, that's in comparison to the without encryption computation, we found that the overhead is actually less for a more complex design, and the reason for this is because in our design we chose a configuration where we have two separate decryption functions to simultaneously decrypt both our instructions and data. So we also implemented this onto a Zinc UltraScale FPGA. So the FPGA utilization is dependent on the configuration of the design. So these figures show for quite a small batch size. So here we're using a 32-byte batch size with 4 cache lines and a key table where we've used 3 enclaves. And the majority of the utilization is based on the actual encryption core itself, which corresponds to a 6% increase in the number of LUTs, 2% increase in the number of flip-flops, but there's also a reduction in the frequency of around 6 megahertz. But As I said, this is a proof of concept design at the moment, and further development, we hope to be able to optimize this in the future. So that's the end of presentation, just if anyone has any questions.
Thank you for the nice presentation. Are there questions?
Thanks for the nice talk. I was wondering if your seal primitive or the Cherry seal primitive has measurement hash associated with it. You mentioned an untrusted operating system. So, I mean, does the threat model include corruption of the code inside of the enclave?
So when it does the decryption, it will check the authentication tag to make sure that they match up.
Okay.
So, and if it doesn't match, then it'll create an error. And so yeah.
So there's effectively a check to make sure that it wasn't corrupted.
Yeah, that's right. Yeah.
All right. Thank you.
Yep. There's one more question.
Yeah, thanks for the nice talk. So I have a question about the keys. You mentioned every enclave has a different key. Given that you have capabilities and associated to every pointer, what's the need for different keys?
So the need for the different keys is the fact that sometimes you might have overlapping capabilities, which could be generated either accidentally by the system or by some kind of adversary. And so you don't want someone to gain access to the same data. So that's why you'd need separate keys.
Okay, thanks.
So there's one more question. Yes, please approach the microphone.
Hi, thank you for the talk. I'm wondering how the keys are stored in the management and generation unit. Because you said like every enclave has a different key, so how does if like the keys wouldn't fit maybe, how the overflow would work if an attacker would create many TEs with many O types?
So at the moment we have a limitation on the number of enclaves that we can generate, and you can set that as a hardware configuration when you build your hardware. And then if it goes beyond that number that you have available, then it will create an error in your system and send that back to the software.
Okay, thank you.
Your enclaves have a data segment, so I think they can be stateful. But I don't quite understand how that works. If I run some TEE code and it updates its own data, does it re-encrypt the whole data chunk?
So are you asking whether it can re-encrypt the external data once it's been encrypted?
Yeah, I have like a pin count. I have a number of times you entered the wrong pin in my TEE, something like that.
So I'm not quite sure what you're asking there.
Assume can I have a stateful TEE that updates its states in response to invoke instructions?
I think we'll just talk about the question offline because I'm not quite sure I understand what you mean.
Okay, I'm sure. Sorry.
Okay.
So maybe one last question from my side. I understood that you have authenticated encryption and it's randomized encryption as well. So many of the commercial TEEs actually just use deterministic encryption and reduced integrity protection or no integrity protection. How do you think this would affect you showed that there's quite some performance overhead because of the authenticated encryption. How much would it be reduced if you dropped integrity protection and randomization in the encryption?
So I guess that would depend on, so at the moment it depends on the batch size. So that's how much you encrypt in one go. But if you got rid of the authentication, then you wouldn't need that to be stored at the end of your encrypted data. So, yeah, I mean, it depends on how much you're encrypting in one go.
All right. Thank you. And yeah, let's thank you one more time. And with that, we move to the next presentation. It's KeyVisor, a lightweight ISA extension for protected key handles with a CPU-enforced usage policy, and will be presented by Jan-Philipp Thoma.
Yeah, thank you very much, Thomas. Yeah, it's my pleasure to present our paper, KeyVisor. It's a joint work with Fabian Schwarz, Christian Rosso, and Tim Gunesu. So, as you all know, anything we do with cryptography, it's very essential to protect the cryptographic keys. And no matter what kind of algorithm you're using, if you don't protect your key, then essentially the encryption is worthless. And we noticed that current CPUs offer very limited opportunities to assist you with protecting the secret keys in hardware. And they can potentially be compromised through memory-based attacks like buffer overflows, through microarchitectural side channel attacks, Spectre, Meltdown, or cache side channels, through any kind of malware and many more. So the question we ask ourselves is really, what can we do to make CPUs help us protecting secret keys? And our solution is called KeyVisor. It's an instruction set architecture extension that protects the keys in hardware. And in a nutshell, it works as follows. So the KeyVisor extension embeds into the CPU microarchitecture. And the key idea is that we wrap user keys for encryptions in so-called key handles, and these key handles are protected by a CPU internal key, which we call the visor key. Yeah, so the CPU has like a root of trust that helps you protect your user key in the hardware. And the key benefit of KeyVisor is that in these key handles we can define attributes that help you define how and by whom the key handle can be used to perform encryptions and decryptions. Now, let's have a look at what a key handle looks like. So in our proposal, key handles have 64 bytes, and we use a combination of authentication and encryption to make sure they cannot be tampered with, and the user key is protected. So in the bottom figure here, you can see the layout of the handle, and you can see that we have the first 16 bytes for the attributes. So we have some flags that basically indicate in which mode we are operating. Then we have some bits that help you define the privilege levels from which the key handle can be used. So for example, you could be defining a key handle that is only usable from supervisor mode. Then we have foreseen a section for the algorithm. So in theory, you can implement multiple hardware encryption algorithms in your CPU. And then you can allow the user to choose which algorithm is used for data encryption. Then for the cryptographic attributes, we have things like allow encryption and allow decryption. So with KeyVisor, it's possible to say, here's a key handle, it's only valid for encryption, or it's only valid for decryption. And then in the feature map, you can define things like the lifetime of the key handle. You can bind it to a specific process, or you can define usage counters. So for example, you can say you can only decrypt 3 times. Then the next 16 bytes are the initialization vector for the handle encryption. This is essentially a unique number that also will be used later as the identifier for the handle. Then we have the GCM tag, which basically provides authenticity for the flags. And finally, we have the encrypted user key, and this user key is basically what is used to encrypt the data that you want to encrypt. and it's protected by the CPU internal visor key. Now, let's have a look how you would go ahead to generate a key handle. So therefore, first we assume you have a process running and you want to request a key handle. So you would use a special instruction that we added to the RISC-V instruction set architecture. And you would provide the attributes or the feature map to the CPU via memory reference. And for the user key, you have basically two options. So first option would be to also provide this via memory mapped I/O. This, of course, has the advantage that you can have a shared key between a third party and your process. However, the disadvantage is that at the time of, let's say, instantiating the key handle, of course, you need to have the user key in your programmed memory space to basically provide it to the CPU. A way to get around of this issue is to use like trusted execution enclaves for this. But you can also well imagine a scenario where you say, okay, at instantiation time, I'm sure that my system is not compromised. Then I give it to someone else, and at later stages, I don't trust it. So then you have the protection through key handles. Another option is to generate the user key in hardware. So there, the user never gets to see the key, and the CPU handles it internally, which is obviously more secure from this point of view. But you cannot really easily share the key between multiple parties. So then when we have all the settings decided, then the CPU authenticates the attributes and encrypts the user key using the CPU internal visor key. And as a third step, we register our key handle in a CPU internal memory space, which we call the handle cache buffer. And for this, we use the initialization vector because it's a unique number that essentially identifies the key handle uniquely. And then in the final step, the key handle is returned to the user process via memory reference, and the user can then use this handle. So some of you may be thinking, wait a second, key handles, I may have heard of that before, because there's Intel Keylogger, which essentially provides a similar thing. However, there are several limitations that we get around with KeyVisor. So the advantages of KeyVisor are that you can revoke specific keys. You can bind keys to processes or trusted execution environments. You can also say from one process, I want to create a new key handle that is bound to another process. So you can basically do key distribution to other processes. You can enforce policies like encrypt or decrypt only. You can enforce usage limitations based on timers or usage counters. And also you can restrict the usage to specific privilege levels. So KeyVisor is much more versatile than the current solution that Intel offers here. I'd like to go through two examples of how the attributes can work and how the usage of the key handles can work. And the first one would be for the encrypt-only attributes. So we assume that the user has a key handle, and since the attributes are stored in plain text, the user can see what are the attributes on that handle, and he can then see that it's probably an encrypt-only or decrypt-only handle. So then the user goes ahead and uses a special instruction to request the encryption of a plain text, and the plain text is provided as a memory reference. So you say, encrypt the data that is stored at address X, and it has a length Y. So this way you can basically provide arbitrary length plain text. Then the CPU goes ahead and verifies the authentication tag in the key handle to verify the attributes that are set. And if this is valid, then the user key is decrypted from the handle, and the decrypted user key is then used by the CPU to perform the action on the data. Now for the second example, I want to look at revocation. So let's assume a user wants to revoke a key handle. And therefore, it's first checked upon execution of the revoke instruction whether the user is actually a valid user of a key handle, so you cannot just go ahead and revoke any key handles that you don't own. And if you're a valid user of this key handle, then the handle ID will be removed from the handle cache buffer, so the internal CPU memory. The handle is only valid if it's stored in that internal memory. So next time you try to use that handle, there will be a check, it will be noticed that the handle is no longer valid. Now, in these two examples, you saw that there are basically two different types of attributes. The first one being handle-based attributes that are stored in the handle itself, and then we have CPU-based attributes. So what is the reason for that? Of course, ideally, we would like to store everything in the handle because then we could spare some hardware overhead and wouldn't have to have this CPU internal memory. Furthermore, if the attributes are stored in the handle itself, then it's very clear from the handle what you can do and what you cannot do with the handle. And it works well for some attributes like encrypt only or the lifetime, but it doesn't work for other attributes. For example, for the revocation, you can imagine that you have multiple copies of the key handle in your memory. So if you would try to revoke the key handle by just, setting a bit in the handle, then you would have to invalidate all of the copies of that handle, and there's actually no way to search for all of these copies. So you have to have that in the CPU. And for process bindings, it's a similar discussion. Here we use in our implementation the ACID, which is the application, the address space identifier, or the physical memory protection ID. And of course, we don't want these data to be part of the handle because we don't want it to be leaked to user space. So it would be a bit of a problem if you leak your page table address to user space in these key handles. So we put them into the CPU storage. Of course, in this scenario, you could also imagine that you encrypt the ACID and put it into the handle, so that would be a different option. But this would create a little bit of additional runtime overhead, which we wanted to avoid. So looking at the hardware implementation here, we implemented this to a RISC-V rocket chip CPU. And you can see we have an interface for the opcodes and the registers, which are used to perform the different functions and to provide the memory references to the plaintext, to the key handles, and to the attributes. And then in the keyvisor extension, we have most prominently the AES GCM unit, which is used to pack and unpack the user key from the handles. And it's also used to encrypt and decrypt the actual user data once the user key has been unpacked. So then we have our central, let's say, steering unit, which stores the CPU internal visor key. We have the memory mapped I/O interface to basically communicate to the rocket chip and make it usable. And then finally, we have the CPU internal storage, which is our handle cache buffer, which we implemented as a two-way set associative cache with 64 cache sets each. You could do this any way you like, but with the cache structure, let's say you spare some bits, and you get a bit better performance out of it. So looking at the numbers, we implemented this on a Xilinx Alveo FPGA using the ChipYard framework. And as you can see, we measure a total overhead of about 16%, which seems a lot on first glance. However, similar to the previous talk, most of that overhead comes from the AES GCM unit. So if you have a CPU that has this AES GCM accelerator anyway, then you would spare about 80% of the overhead here. And in addition, you should consider that the rocket chip is a really, really small CPU. So if you have a more complex CPU, then the percentage overhead goes down by a lot. Overall, the main effort here is to have that hardware crypto unit. So for performance evaluation, of course, that also heavily depends on what kind of hardware implementation for the AES unit you choose. And you could imagine all kinds of area performance trade-offs here. In our implementation, the handle-based encryption took between 188 and 421 clock cycles for data between 4 and 200 bytes, which is like not really meaningful numbers without any comparison. The more interesting number here is the constant overhead that we have, and that is the overhead for unpacking the user key from the key handle and validating the key handle. And as you can see, like if we only encrypt 4 bytes of data, then we have about 100% overhead. If we go for 200 bytes, then it's much less. And we found that for typical TLS package sizes, we have around 6% runtime overhead. And that is for the comparison against a direct hardware implementation. So in comparison to software implementation, we are faster anyway because hardware implementation outperforms it by quite some margin. So for the final part of my presentation, I would like to focus on one of the use cases. In the paper, we discussed 3 different use cases and applications where KeyVisor can be useful to implement things that wouldn't be possible without it. And here I would like to look at the read-only network intrusion detection system. And you can imagine in this very typical scenario where you have a client computer that is connected to the internet, and they want to have, let's say, an encrypted TLS session to securely communicate. And then the computer is sitting somewhere in a local area network that there is an administrator who wants to make sure that there's no malicious traffic. So what they do is they implement typically a next generation firewall or a network intrusion detection system, which breaks open the TLS connection and inspects the content. But of course, for this, they need to have the key. So either you break the connection at the IDS, or you somehow provide the key to it. And of course, if you don't trust your local network administrator, or if someone manages to attack the NITs, then the intrusion detection system could manipulate the traffic and could change the data that is being exchanged between the client and the internet. So the solution with KeyVisor is that you can instantiate a read-only key handle on the NITs. So then you can basically guarantee that the NITs can only inspect the traffic but not modify the traffic. And of course, here it's important how do you share the key? How do you make sure that the right key gets into the network intrusion detection system? And for this, we have in the paper a proposal to use a remote key provisioner based on a trusted execution environment. So you can basically do remote attestation of the setting up the key handle, and then make sure that your NITs has read-only access to your connection. And with that, I'm at the end of my presentation. Thank you very much. The source code is available on GitHub, so you can try it yourself. And yeah, happy for any questions.
Thank you, Jan-Philipp. Other questions? I see there's one.
Thanks for the wonderful talk. This is just a trivial question. I saw that in your resource table that AES is taking a lot of space. Then I also saw that one of your slides, seems like you have a plan for the CHES and the ESCON as well. So do you think that it will help on reducing the resource consumption?
Yeah, so good catch. Yes, the AES core is the largest part of our implementation, and of course, if you would use, for example, ESCON then the hardware overhead would reduce by whatever the amount of your implementation is smaller. The thing is, so we planned for multiple different algorithms that you can use to encrypt and decrypt data. Currently, in our proposal, the wrapping of the key handle always uses AES GCM, but of course you could change that to any other authenticated encryption algorithm and reduce the overhead.
Thank you for the presentation. I have one question. As far as you know, the TLS key generation is generated from the key exchange, not from the key generated from the hardware, right? So I want to some explanation. What's the relation between the key that generated from the hardware with the TLS generated AES key that shared from the key exchange mechanism? Thank you.
So in the case of the TLS inspection, you cannot use the hardware-generated keys, but you have to use the user-provided keys. So we have the option for the user to say, this is the key that I want to be wrapped in the key handle. And you can basically then do the remote provisioning on the network intrusion detection to make sure that the right key is getting there. And you can make sure that it isn't leaked through, let's say, a combination with a trusted execution environment and remote attestation.
Means you generate your TLS key from your visor key, is it?
No, we don't generate the TLS key from the visor key. So the encryption key, the TLS key, can be instantiated using the traditional TLS handshake. And then the user can say, I want to use this key for my TLS session. I want that to be wrapped in a key handle. And then this TLS key is encrypted by the visor key to put it into the key handle to protect it on the ISA level. Yeah.
Okay, thank you.
Thank you. Thank you for the presentation. Basic question. So how do you check the correctness? Because this is quite complicated key change protocol, whatever you want to call it. How do you check for weaknesses or that you don't violate any of your threat model assumptions?
You mean the correctness for the basically for the handles?
Yes.
So we have basically all the attributes are authenticated using the GCM. So there, like if you change any of the attributes, if you manipulate them, then it will be detected. And for the user key, like that is wrapped into the key handle by encryption. So as long as there's no, let's say, implementation errors, of course, then this is like you cannot manipulate the handle. Of course, if you want this to be in a, let's say, a real CPU, you should have some kind of functional proof that what you implemented is actually secure and you don't have any, let's say, I don't know, corner cases where you can use a key handle differently to what is defined by the attributes. Does that answer your question?
Yes, or like the sequence you have to use before a key is released or a page is released. I mean, all of this seems to be very critical, no? Like in your example, your last example.
Yeah, so yes and no, I guess. I mean, if you have the TLS key instantiated between the two parties, then actually all you need to do is to create a handle for this key. So there's not much, I guess, that could go wrong in this step because you just provide it to the CPU, and then it generates a key handle for the data you provided. So I don't think there's much that can go wrong at this point.
Okay, thank you.
All right, so I think with that we conclude our first session today. Let's give a big hand to Jan Thomas and the other speakers of the session.